Okay, now that we have seen that the quantity q by t is behaving like a state function, right, and it is getting conserved in in the reversible Carnot cycle, that was observed, we derived that the quantity q by t was getting conserved in the reversible Carnot cycle. Now Clausius, one of the great chemists, he came up with this idea that okay, any reversible process, you take any reversible process, he says for any reversible process the quantity q by t is being conserved. Okay. Now how can we justify that? How did he justify that statement? That's the topic of discussion with which we are going to start. So the general idea is that any reversible cycle, like if you have any reversible process, any reversible cyclic process, can be represented as a combination of Carnot cycles. Like that's the big idea behind the logic, that q by t will behave like a state function for any reversible process. Okay, like any reversible process. So these are the two diagrams that will help establish this. Now the diagram on the left is just any process. Okay, like so any path. So this is a PV path, any PV path. Okay, with this green line. So you can produce this green line, that any process can be produced by a combination of an adiabatic and an isothermal process, like any small process. So imagine that these purple lines and the blue lines become smaller and smaller. So at one point, all those small adiabatic and isothermal process will become so small that it will absolutely replicate this excuse me, this green process. So that means any PV path can be represented as a summation of several isothermal and adiabatic processes. So this is one of the key ideas in here. Okay, so understanding this, we see a reversible process. Okay, let's say this is a reversible cycle. So this is a cycle. So now, so this cycle, based on this idea, what I'm saying is what Clausius said actually is that we can divide this cycle into very small Carnot cycles. So like this entire circle, this yellow circle, can be divided into small Carnot cycles. How is that possible? Now, if suppose we divided these into several small Carnot cycles, so all these quadrilaterals that we see in here are several Carnot cycles. So when you have all these Carnot cycles, what happens is all these processes, all parts inside the process, they cancel out. To visualize this, like how all parts inside this is cancelling out, it can be understood if we just look into one of these pairs. Okay, so if you look into these pairs, this is a Carnot cycle, this is a Carnot cycle. So you see the ones that are adjacent to each other are getting cancelled out. Similar thing will be happening if you have one in here. So in this case, again, the steps adjacent to each other will be cancelling out. In here, again, things adjacent to this will be cancelling out. And in here, again, things in here adjacent will be cancelling out. So you see all these that are inside are getting cancelled out. So all these small steps that are there, all these small PV paths that are inside are getting cancelled out. What remains is the outer circumference. So what actually remains is just this yellow curve. So first what we did, we divided this yellow curve, this yellow thing, into several small Carnot cycles, right? And then we saw that all the steps that are inside this circumference, or inside this circumference, are getting cancelled. So what remains? What remains are all those small Carnot cycles that are there on the circumference. So we only have, so in here I have drawn the Carnot cycles as big quadrilaterals. So imagine like small quadrilaterals that are actually making up these the circumference. So all the Carnot cycles that are just on the circumference are getting preserved. So they are not getting cancelled out. Okay. So all parts inside are getting cancelled out, and we are left with the outer circle, which are made up of infinite number of Carnot cycles. Okay, so that is how the idea that any reversible process can be represented as a Carnot cycle is coming from this idea. Okay. Now we saw for a Carnot cycle that Q over T was getting conserved. Okay. So now if we have small q's for those small Carnot cycles, the del Q by T for all these individual small cycles will be conserved. Now if you integrate all those, okay, over the entire cycle, okay, over that entire cycle, that will be 0, because this is behaving as a state function, as we discussed before. Q by T is behaving as a state function. Now any state function, if you integrate it over a cycle, so you start somewhere, go around a circle and come back to the same point, the state function, the value of the state function will be 0. Okay. So this is why the value Q by T is conserved for this entire cyclic process. Okay. Now this value, the del Q by T, will be represented by this. Okay. So if you have del Q reversible, now if you have a reversible process, so the del Q will be represented by del Q reserve over T, right. So this quantity is basically ds. Now what is S? Now this S is the entropy. So this is how they came up with the idea of the entropy. Okay. Now entropy is a state function, as we discussed, because when you are going it around a cycle, it is coming out to be 0, and this is an extensive variable. Now remember what an extensive variable was. An extensive variable is something which is dependent on the size of the system. So as you have more and more quantity of material in the system, entropy will be more. So you have more quantity, you will have more entropy. So the entropy of the system will be dependent on the size of the system. So entropy is a state function and it is an extensive variable. Okay. So Q by T. So this is how we came up with the idea of entropy. So we knew that Q by T is a state function, and we gave a new name to that state function and we call that entropy. Okay. Okay, Q by T is entropy, and del Q of any reversible process by del T is being represented by ds. Okay. Now there is a small idea that we introduced in here, Q reversible now. Okay. So the processes can be reversible and they can be irreversible processes. Okay. All right. So let's suppose you have a reversible process and in which you have a system. You have a system which is undergoing a reversible process. Okay. Now this system is undergoing a reversible process. So during a reversible process, entropy is not being created. So you cannot create an entropy in a reversible process. Now in a reversible process, entropy can be exchanged. Okay. Entropy can only be exchanged in a reversible process. And how will the system, with what will the system exchange the entropy? With the surrounding. Okay. So in a reversible process, entropy is being exchanged between the system and the surrounding, and that kind of entropy is represented by DES. Okay. This is what is being exchanged. This is the exchanged entropy. This is not being created. This is not being created. This is exchange. And why it is getting exchanged? Because in a reversible process, you cannot create entropy. You can exchange it between the system and the surrounding. So in a reversible process, what will happen? If the system is getting more entropy, it is getting more entropy from the surrounding. So the surrounding is providing it the entropy. So the summation of the entropy of system and the surrounding will be equal. Okay. So DES of the surrounding plus DES of the system will be equal. So if this loses entropy, this gains the entropy. If the system loses entropy, this gains entropy. So the entropy of the entire universe remains constant if you have a reversible process. Okay. Now this is one of the ideas. Now the flip side of the idea is in any irreversible process, so you have any irreversible process, the system will be producing entropy. So in any irreversible process you will create more entropy. Okay. So now that we have seen that okay, the universe can have many different kinds of processes. It can be reversible, it can be irreversible. So in reversible, the entropy can be exchanged, but in an irreversible process you create entropy, and the more irreversible a process is, the more entropy is being created. Now this is also the second law. This is another way of representing the second law, that for a reversible process the entropy remains same. So right, if this is the exchange entropy, there is another way of representing the created entropy by DIS. Okay. So the DIS in a reversible process will be 0, right, for reversible, because you do not create any new entropy in a reversible process, but DIS will be greater than 0 for an irreversible process. Right, you are creating more entropy in an irreversible process. And what will be the total entropy of a system? So DIS plus DES. So you have the universe, okay. So you have the universe, and in the universe there are some reversible processes going on and there are some irreversible processes going on. So in reversible process you are not creating any new new entropy, but in the irreversible you are creating this new entropy. Okay. So this is DES, this is just the exchange. So this value is not getting changed. It is either going from the system to the surrounding or from the surrounding to the system. So basically DES for the entire universe is remaining constant. This is not changing. But the DIS is getting exchanged, is being created. Therefore, the total entropy of the whole universe is always increasing, because there is nothing that is decreasing the entropy. It is either getting exchanged in a reversible or getting created during an irreversible process. So the total universe, the entropy of the total universe will always be increasing. Why? Because there will always be some irreversible processes going on in the universe, and therefore those processes will increase the entropy. The reversible process don't change the entropy, but the irreversible processes are increasing the entropy, and therefore the entire entropy of the universe is always increasing. And this is also another way of representing the second law of thermodynamics.